In this lesson, we're going to look at the relationship between pressure and volume for a trapped gas. And that relationship is formally described by Boyle's law. We'll get to what exactly Boyle's law states in a moment. Here we have a simulation, and just now I'm going to actually run it, but let's speak about it first. We have a trapped gas inside this container. The lid is movable, so I can push harder, obviously not really me, but in the simulation it says if I push harder on this lid, and that's going to compress the gas, it's going to squash the gas into a smaller volume, and then I want to see what effect does that have on pressure. Now volume, means space. So if I push down the lid, then the gas has less space, less volume. Pressure refers to force per area, and it's related to how much the particles hit against the sides of the container. So while I now run the simulation, I want you to see what happens to the rate at which the particles hit against the sides as I compress the gas. So let's watch now. Can you see that as the gas particles are squashed in less and less space, they hit the sides more and more? So as the volume of a trapped gas is decreased, the pressure that the gas exerts increases. So this shows that there's an inverse relationship between these two variables. When one is big, the other one's small. Now, does inverse relationship also mean inverse proportion? It might be or it might not be. What does inverse proportion mean? Inverse proportion means that as one variable is decreased, the other increases by the same factor. So let's look at some ideal easy numbers to test whether volume and pressure are really inversely proportional to one another, not just inversely related. So we're going to keep temperature and amount and type of gas constant throughout this investigation and in this data, and we're going to vary volume, and we're going to see how does that affect pressure. So volume is our independent variable and pressure is our dependent variable. So we're asking the focus question, how does the volume of a trapped gas affect the gas's pressure? Now we've already seen that a volume change causes a pressure change. When the gas particles are squashed together more, then they push harder. But volume and pressure are interesting in that there's not just a one-way causal relationship, there's a two-way causal relationship. So a pressure change also causes a volume change. We'll speak more about that just now. So the question could also have been, how does the pressure exerted on a trapped gas affect the gas's volume? Because anyway, I can't make the volume smaller except by pushing harder on the lid. When I push harder on the lid than the gas pushes on me, then I make the lid accelerate downward, and that compresses the volume. But then the volume stays as it is once I've reached the volume I want, and at that new volume, the gas is pushing harder upward on me than it was before I decreased the volume, but it's pushing just as hard as what I'm pushing. So the question could also be said, how does the pressure exerted by a trapped gas affect the gas's volume? All of those questions are correct, and all of them are answered by Boyle's law. So let's look at some ideal data. We have volume and we have pressure. Now, volume is measured in various units. One of them is decimeters cubed. Pressure is also measured in various units. We get kilopascals, atmospheres, pascals, and so on. But to be simple, so that we can see the patterns nicely in our data, for now, we're just going to use a simple unit called units. So let's say that when the volume of a trapped gas is 5 decimeters cubed, then the pressure it exerts and the pressure we have to exert to keep it at that volume is 1 unit. Now let's halve the volume of the gas, and to do that we would need to apply a pressure of 2 units. And so on. As we increase the pressure that we apply, the volume that the gas takes up is less and less. Now look for patterns in this data and use those patterns to solve for the unknown value here. Let's compare line 1 and line 2. We've halved the volume. As a result, the pressure has doubled. from line 1 to line 3, we've thirded the volume. 5 divided by 3 equals 1,67. As a result, the pressure has tripled. 1 times 3 is 3. From line 1 to line 4, we've quartered the volume, and the pressure as a result increases 4 times. We've decreased the volume 5 times. In other words, 5 divided by 5 gives us 1. And as a result, the pressure has increased 5 times. 1 times 5 equals 5. We don't only always have to compare with the first line of data. For example, we could compare any two lines, let's say the second and the fourth. 2,5 divided by 2 gives 1,25. 2 times 2 gives 4. Let's compare line 3 and line 4, and let's look at the pressure first, because pressure can also be the independent variable. Volume doesn't have to be the independent variable, because these two variables are related causally. 3 times 4 over 3 equals 4. We can see that easily because the 3 cancels from the top of that fraction and the bottom of that fraction equals 4. But that's the same thing as saying 3 times 1,33 equals 4. 4 over 3 is the same thing as 1,33. 3 times 1,33 equals 4. And 1,67 divided by 1,33 equals 1,25. Or we could say 1,67 divided by 4 over 3 equals 1,25. That's the same as saying 1,67 times 3 over 4 equals 1,25, because in divide we tip in times. So using those patterns, what is the missing number? What would the volume of this gas be when its pressure is 6 units? To answer that, we need to ask ourselves, well, how many times have we increased the pressure from, let's say, line 1? That's the same many times as the volume will have decreased from that line of data. 1 times 6 equals 6, and therefore the missing value is found by 5 divided by 6. And that gives us the answer of 0,833. The unit is decimeters cubed, because all these units are in decimeters cubed. There's another pattern that we can use to solve for this. Notice that always the volume value multiplied by its associated pressure gives a constant value. In this case, that constant value is 5. 5 times 1 equals 5. 2,5 times 2 also equals 5. 1,67 times 3 equals 5. 1,25 times 4 equals 5. Obviously 1 times 5 equals 5. So whatever the missing value is times 6 must also equal 5. So what must the missing value be? We do a bit of algebra. V times 6 must equal 5. Clear the fraction by dividing through both sides by 6. Make V the subject of the formula. 5 over 6. 0,833. Again, we know that the unit is decimeters cubed because all these volumes are in decimeters cubed. So here we found the same answer again, using just this other method. In fact, it's not another method. Both of the methods that I've shown work with proportion, and so it's just two different ways of showing the same thing of inverse proportion, because volume and pressure are inversely proportional to one another, and that's why these patterns work. Now let's put this pattern of inverse proportion into an equation so that we can solve things nice and neatly. Let's call the volume in line 1 V1. And the pressure associated with it P1. We can see that in this particular case, V1 times P1 is equal to 5. Now let's take line 2's data and call it 2. V2 and P2. V2 times P2 also equals 5. So since both of these equal the same thing, these two must equal one another. V1 times P1 is equal to V2 times P2. We don't have to write the times, we can just put things together. V1 P1 equals V2 P2, and we can change them around if we want to. And so we could write this as P1 V1 equals P2 V2. And this is the form in which this equation is usually put. And sometimes this equation is called Boyle's law. It simply shows that pressure and volume are inversely proportional. So let's use this a little bit. Let's take lines 1 and lines 5 to check if it also works for other lines. P1 V1 also equals P5 V5. We can see both of those equal 5. 5 equals 5. What about lines 3 and 4? P3 V3 equals P4 V4. Substitute the values and you do the calculation. You'll see that each of them equals 5. 5 does always equal 5. So using this equation, let's solve for the unknown value. Now we can use anything as a comparison state. Notice we always have two lines. One line to compare against and one which has an unknown value. So it doesn't matter which line we take as our comparison. Let's take line 4. We also don't have to call this V4, P4, V6, P6. It doesn't matter what we call 1 and 2 and so on. As long as V1 is associated with P1, that's the pressure when that is the volume. And P2 is the pressure when the volume is V2. Those numbers must correspond. But it doesn't matter what we call V1 or V4 or V5 or V2. So we could call line 4 as V1 and line 6 as V2. So we have P1 V1 equals P2 V2. We substitute the values. 4 times 1,25 equals 6 times V2. Now we need to solve for V2. We make V2 the subject of the equation and we find the answer 0,833. We know that the answer's unit is decimeters cubed because V1's unit was decimeters cubed. In this equation, P1 and P2 have the same unit as one another. V1 and V2 have the same unit as one another.